just start for now. So okay, so the objective of today is like going like kind of rough idea of like paper reading, or it's more like paper skimming. So of course you can read a paper and read it like line by line, word by word, until you finish. But that sometimes is very inefficient, and especially if I tell you, okay, I give you a list of papers, or I tell you a topic, and you don't know anything about that topic, you may first need to get a rough idea of, okay, find some papers and then see which papers are the ones you should focus on. So that's the first thing we usually do, like it's looking at like the title of the paper. um, in this case, for most of you, will be working on fine-grained image recognition. So most of the papers you will read, they will have some image recognition or image classification or some visual recognition, visual classification, some like title related to that. For example, for you, then each of you has like a specific topic. So Kisun, like you may need to read things that say something like parameter efficient something. Uh, and then for Jensen, you may need to read something like um, token fusion or something. Um, so that's the first thing we do. Like if you're given a list of papers or you're looking like Google up something like a topic, you will get a lot of paper titles. So you need to like efficiently look at the titles. Then aside from that, I would say one thing that you can do is you can just quickly check the paper sections, like just to see, just to get a rough idea of how long the paper is, and kind of like you can do it like very quickly. And then after that, there's two things that are more important and you probably need to look at in more detail. One of them is the first figure. And this is not always for every paper, because some papers, they do not write the most important thing in the first figure. But a lot of paper, usually they will write the most important information, like maybe it's either like some results that are very important, or maybe some overview of whatever they are working with or the problem that they are working with. Usually it's in the first figure. Then aside from that, the abstract. And the abstract is, at the beginning, it can be very hard to read because abstracts are short, usually one paragraph, but abstracts are very dense in terms of information. And usually abstracts would cover three things. They would first describe the motivation or the problem that they want to solve. Then they would describe the problem that they proposed, and then they would like summarize the results usually. So abstracts use a lot of like technical terms that you may not be familiar with. So reading abstracts can be difficult, but it's something that as you read more abstracts, you will like, and you read more paper, you will kind of be familiar with what they are talking about, and it should become much easier. So usually, once you have like read a few papers, if you then want to read a new one, you will like look at the title, look at the abstract, look at the first figure, and you can get most of the idea of a paper through those three things. There may be some cases where you need to do like an in-depth presentation. You want to present to your lab, or I don't know, to like a class or something. And then in that case, you may need like to read like the rest of the figures, tables, and some specific section. Um, so I think that's kind of like the general idea. In order to like kind of like get you familiar with what kind of things do we look at when reading papers, today I will go through a few examples, both like in-depth reading of like a whole paper, and also like going through short sections. And the first one I want to go through is AlexNet. I don't know if you have taken a class on deep learning, but if you have, everyone, you would read about this paper at some point, or someone will present out this paper at some point. Because it's probably the paper that brought deep learning back to the spotlight after a lot of years that it was kind of in the shadows. So starting with the abstract, again, I mentioned like abstracts can be like very dense. So I kind of already like highlighted for you kind of what I want you to get from this paper. So you have the first contribution of this paper. They say they train a large deep convolutional network, and it has like, they describe it and they say it gets good results. That's the first contribution. So they are the paper that they train a large convolutional CNN. Then the second thing is they say to make training faster, they use non-saturated neurons, which we will talk about that later. It's what we call an activation function. Then in order to like make it this like fast, they use like a GPU implementation, which is something related to okay, like basically making good use of the hardware. And then finally, they propose a thing called dropout, or they use a technique called dropout for reducing overfitting. Um, and these are like the four main contributions of AlexNet. And now we'll go going through like the whole paper, like kind of like section by section. So in the introduction, usually you would like first describe the problem you want to solve, like the first paragraph. In this case, they are talking about the problem is image recognition. And they are talking about like, yeah, small data sets, larger data sets. That's kind of what's image recognition and what are the current like challenges. Then they mentioned that, okay, like therefore, like sometimes you would like talk about the limitations of the current approaches. And in this case, they mentioned that, okay, if you want to learn for many images, in this case, the task was ImageNet, so it was millions of images. You would need a model, like a large model, that can actually be able to process all of that information and learn about all of that information. So that's what they do in the second paragraph. They basically describe an idea of something called a convolutional neural network, CNN. And then they say that, okay, their capacity can be controlled by varying their depth and breadth. Um, and basically, then after that, they say that, okay, in the past, the problem with CNNs was that they took too long to train. So the computational cost was the limiting factor. But they say that currently we have GPUs now. So with GPUs, you can like train these models efficiently, basically. And then some papers, like then at the end of the introduction, they would summarize their contributions. In this case, this last paragraph, they summarize the things that they did. Kind of they list them out like, okay, this is what we did, and this is in this section or something. And in this one in particular, they also included a limitation. It's kind of also like some possible future work. In this case, they say that their limitation is like, okay, the current GPUs, and they expect the advances on hardware to further improve uh, yeah, this problem. By the way, if you have any questions at any point, just ask. Just ask immediately, or you can ask at the end. Then okay, now this second thing, like going into the paper itself, their first contribution. So as I mentioned, the most important contribution is like a CNN, but they didn't propose CNNs. CNNs actually were proposed in 1989. And what's a CNN? A CNN is a stack of what they call a convolutional layer and pooling layers uh, that are like a kind of like neural network with learnable parameters designed specifically for, in this case, for like 2D images, because they apply uh, convolutional filters at different point, and they are supposed to like learn these parameters. So this was proposed first by Jan LeCun in 1989. But at that time, they were limited by computation. They didn't have GPUs at that time. Like much more recently, like in 2011, uh, this paper was published on, like AlexNet was published on 2012. Like another group from like university, I think in Switzerland, led by this guy, Georgian Schmidt-Huber. They also proposed CNN, but they tried it only on this small task of digit recognition. But they say that you could actually like train a CNN on a GPU, and they do it with like 4 layers, and they obtain good results. And this was published the year before AlexNet in February of 2011. So the biggest contribution of AlexNet was not these CNNs. It was, first of all, proof that it worked at scale. I think that's the keyword on the most important competition for image recognition at that time, which was the ImageNet Large Scale Vision Recognition Challenge. And then by doing that and releasing their source code, basically it made it so that a lot of people got interested in this, and a lot of people began experimenting with this kind of like new technology. And I would say that's their understated contribution, that they did provide source code. because if they wouldn't have provided source code, a lot of this, maybe like this wouldn't have caught up as fast as it did. But because they did provide source code, people who were working on this, they immediately read this paper and they began working on it. And then by 2013 and 2014 and after that, all of the important results in image classification and a lot of other computer vision tasks have been dominated by CNNs since then. And well, there's been newer things right now, but for the next few years, it was definitely dominated by CNNs. Then the rest of the paper, they also like in this section, they describe more in general, like what exactly, how do they design this network and like the specifics of, okay, like the first layer has like how many filters and the second one has so many filters. If you're interested, you can read the paper, but I just want to give you an idea of, okay, yeah, this is kind of like the overall architecture. And as I mentioned, it's basically a stack of convolutional layers and pooling layers and fully connected layers. And yeah, then like there's like a lot of like 2 pages describing that. Then another of their important things that they describe is this ReLU, rectified linear unit activation function. So previously, before this, they mentioned that what they describe in this paragraph is that people in the past they use 2 activation functions called sigmoid and hyperbolic tangent, which are shown in this figure. And they call this function saturating because you see if the value of x is below a value or it's after a value, it's just it will stay like within this range of like 1 to 0, or in this case 1 to -1. So it cannot like go above or below this value. So that's why we call it saturating. In this paper, I propose this ReLU activation function, which if it's below 0, it will be 0. But if it's above 0, it will be the same value. And it can be like basically any value from 0 to infinity. And they say that the reason that they propose this or that it helps is because when you have large data sets, you want it to have faster training, and therefore like a non-saturating function like this one leads to like larger gradients for backpropagation and faster training. And then that's kind of like what these plots were kind of describing. Then aside from that, I mentioned that they also had a contribution regarding to the implementation. They say that like GPU limits the size of the networks. So because as I mentioned, someone else had already like done training on GPUs in 2011. So what their contributor is like, okay, they train on multiple GPUs. And they kind of describe like a short like paragraph, like how do they implement that. But the idea is that okay, they do train on multiple GPUs. And then finally, they also describe like a technique called dropout, which they say help to prevent overfitting, which was a serious issue before. And the way it works is they randomly turn off some neurons in the neural network, and they basically they want to force all the neurons to actually learn features, not like okay, just some neurons work and some others they do not do anything. Uh, and then they describe about they talk about this. They compare it to like what's called a model ensemble, because supposedly model is learning like multiple possible models. And technically, this was not their contribution, but this was the paper that broke this technique to the spotlight. This was published on a paper from the same group in that same year, a few months earlier. And aside from that, this paper had other contributions that they describe in the details of the paper. I'm not going to go through them, but if you are interested, you're welcome to go to read at it. Some of them were like weight decay in the optimizer. They mentioned this is important. And then they also proposed a technique called local response normalization, which was supposed to help train like their network, but people stopped using this because it didn't help with deeper nets. So again, most papers they would have like a section on methodology. In this case, the methodology section is spread out across like different parts of the paper. They would have like, but this section usually it would describe things like how do you train the model, like the optimization, and what kind of data did you use, and how did you do like some data augmentation or some pre-processing. Uh, this paper, they describe that across different pages. Like in section 2, they describe the data set. They also describe how do they do the pre-processing. Then they describe like a technique for like data augmentation, basically based on like some random cropping of the images. And then they also describe like the optimization procedure, like what optimizer they use, the batch sizes they use, and weight decay, like why is it important. And then they describe that to train their model, they actually had to initialize it in a certain way, like the parameters. And they also like use some like what learning rate do they use and what kind of scheduler like do they use for the learning rate. And finally, the rest of the paper, it's about results and discussion. uh, Usually you would have like some main results. In this case, the main results are some comparisons on ImageNet across like CNNs and traditional methods, and they basically say that like CNNs perform much better than traditional methods. And then they would also maybe do some ablations, like comparing their method with different variations to see how does it perform better. And then other papers and this one, they also maybe sometimes include some visualization. So in this case, they include some visualizations of what was the neural network learning. In this case, like the different filters. And they say that, okay, yeah, we can see like some of these filters, they look like traditional filters designed in image processing. But the thing is that the network is learning these filters automatically, which is like the biggest advantage of these deep learning models, that they can learn functions that we can design by hand automatically, and they can also learn functions that we probably cannot design by hand. And yeah, the rest of the paper, it's kind of like, yeah, like these results and the discussion of these results. So that's for like the first paper. Um, Now, again, if you have any questions, feel free to stop me. Otherwise, I'm going to go to the second one, which is PGGNet. And the main takeaway from this paper that you should get from today is that depth matters. It's called Very Deep Convolutional Networks for Large-Scale Image Recognition. And this paper focuses on one thing, studying the effect of depth on CNNs. They mentioned that they investigate the effect of the neural network depth, basically by pushing the like different number of layers from 11 layers, 13 layers, 16 layers, and 19 layers. And they basically see that like the deeper networks perform better. So that's their main contribution. And the paper, again, all papers start with the same, like some background. In this case, they are describing like how CNNs have become so important in the past few years. And then they mentioned that the previous work actually was focused on how to improve CNNs, and some different people did like different ways to actually improve them. And in their case, okay, by doing their study on depth, they actually get like state-of-the-art results. Then the rest of the paper, like a lot of the section 2 is describing their model. Again, I don't think we need to go through that, but they basically describe okay, how each layer is designed, both in text, and they also describe it here in a table. Then they describe also like kind of their differences with previous work, and they also like do some discussion on why do they design their network in a particular way. Again, you're welcome to read it, but if not, otherwise, I think like the important thing is that like depth is very important for deep learning. Then there's like a long section on methodology, like description of their model architectures, and also on the design, like some implementation, like how do they do their training, and like so many initialization tricks to train these new deep neural networks. They also like their image pre-processing and data augmentations. How do they test their model, and how do they implement it both in software and hardware. And finally, like the data set that they use. And then again, most papers like they follow like the same structure, like kind of you introduce the problem, you discuss maybe the related work, then you describe whatever you proposed and the data set experiments you're doing, and finally you go through the results. And in this case, the paper was focused on their design, like the depth and how basically adding more layers help the problem. And then they test that on different scenarios, and then they show that consistently, like deeper networks obtain better results. So yeah, that's kind of like the takeaway from this paper. Then there comes ResNet, and I would say this one also proposed something very important. In this paper, they propose what they call skip connections. Um, and what is a skip connection? It's, I will show it in the, like, basically the idea is that if we have a neural network and we have multiple layers, in the past they would just stack layers one after the other, and then they would train the network. And then if we have like an input, in order for the input to get to the last layer, it will have to go through all of the previous layers one by one. This came with a problem that they realized that, okay, there's a point where you begin stacking layers and your results become worse. And that's kind of like their takeaway, that basically if they look at this table, they would say that when they made a deeper network, instead of getting better results, they were getting worse results. And they call this problem like degradation, model degradation. And they are basically wondering why. And they say that it's not because of like exploding gradients or any other things that people were thinking before. They didn't know like why, but they said that one possibility to actually solve this problem is by, instead of training the like just like layer after layer, you would add like what we call a skip connection. So if we can think of this on the right as a neural network layer, like this block in here, what they do is, okay, you have the traditional neural network, and then aside from that, you would add like some connection that you basically add the output of this layer and the original input. So that way we have something like, if we have an input x and we have a block fx, then what we'll be doing is like the skip connection is like the sum of fx plus x. And this is something that is very simple in paper, but it had like a lot of repercussions because it solved this problem that they saw here, where if you increase the number of layers, it will become worse. And actually, it led to like much better results down the line. And basically, they won also like the ImageNet competition for that year. And then basically, almost every single paper after this has been using skip connections because they provide a way to optimize deeper networks, like much more like simply. At the same time, they mentioned in their paper, in their network section, that they were not the first paper to propose something like this. But in the past, for example, there was another paper that also proposed something similar, but they would have like a more complicated way of doing it. And that other paper is called Highway Networks. And it's also from the same group that I mentioned earlier, Jorgen Schmidt-Huber from Switzerland, I think. And this person, he was the author of another very important paper in deep learning called LSTM, something called long short-term memory network, which is something that was proposed, I don't know, in the 90s or something. um, and then basically they were inspired by that kind of design, and in that design they have this thing called gate mechanism. So the gate mechanism, we can imagine it as like, let's imagine that we have this same design, but instead of letting the input go directly, like just adding it, you would add like another like small network or some like what they call a gate to decide if this is going to be added or not. um and they proposed this also in the same year as the ResNet paper. The ResNet paper was released on arXiv of in 2015 in December. And this same group, they proposed this idea in arXiv around the same year, but around May. So these two papers came out very close, kind of half a year in between each other. The difference is that in the highway networks paper, they focused mostly on these MNIST and CIFAR-10 datasets, which are much smaller. In the ResNet paper, they focused on ImageNet, which is an other task, so it's a much more important uh, classification task. It's much more difficult at the same time. And again, I mentioned that the biggest difference is that in this case, the design is very simple. You just add like the input back to the output of this block. In the other case, they still have to train another network to decide if this should be added or not. So I would say that's the biggest difference. And you will see that, well, these two papers, this one is probably the most cited deep learning paper at this point. It has 160,000 citations, while this one has kind of like 2,000. And that's probably because in deep learning, a lot of things people care about results, and results in this kind of task like ImageNet. So because yeah, basically like that's kind of like I would say something that you can see like a trend. Like people care about a lot about the experiments that you conduct in deep learning. Deep experiments are at the core of like deep learning. Um, so it's like a very results based kind of field. Then the rest of their paper, they just describe this residual function idea. They mentioned that the advantage is that there's no extra parameters because you don't need to learn any function to like learn that residual function. And they can mention that, okay, this can be very flexible. And then they describe the rest of their network and also like describe like their motivation. And this is like their network itself. Basically, here we can see on the left like the BGG network, and we see, okay, it's basically like a straight line. Okay, you go from this layer to the next one and so on. Well, in this case, if we add like the residual connection, we would see that now instead of sometimes like each few blocks, you would have like another like input from the previous layer. And that makes all the difference because they mentioned that if you compare these two networks that have the same number of parameters, just the difference is that one has the skip connection and the other one doesn't, you would basically get much better results. And the rest of the paper is structured like that. They basically compare their network when using these skip connections, and then they would say that, yeah, like from this kind of figure, basically the ResNet version, the one with residual net connections, would perform much better in both the deeper and the like shallower layers. And then since then, most papers have been using skip connections in their designs. And the rest of the paper, it's like a very in-depth analysis of how do skip connections solve this like network degradation issue and how to obtain like state-of-the-art results on a few tasks. Okay, so that's been a lot. But I basically what I wanted you to get from that is that results are very important on deep learning. Um, like usually most of the important information on a good paper is concentrated around the abstract and the introduction. And then the rest of the paper, it's a lot of the page, sometimes even half of the paper, it's just focused on presenting results to support whatever method you're proposing. Um, so when you're reading papers, you should like read smart, like basically kind of try to find the important ideas, like why do they propose this or what are they trying to solve? Why do we care about this? And maybe like try to understand what did they propose. But you don't need to like necessarily read through like the whole thing, because otherwise, yeah, there's a lot of stuff that is it will take like too long if you need to read a lot of papers. Aside from that, there's also another paper I need to cover. It's Inception. Previously, I mentioned that BGG proved that depth is important, so deeper is better. This one proved that depth and width are more important. So they like increase the depth of the network by adding like these parallel connections. Um, so that's about the width of the network. And then they also prove like auxiliary intermediate classifiers can be like also useful. So they have this deep network and they would have like a classifier here and a classifier here and a classifier here. So that way you can have like better flow of like gradients through the whole network. So the network, like the earlier layers, can focus on like simpler kind of like tasks, while the deeper ones can focus more on like the details. And like an understated contribution of this paper is that they started this trend of deep learning being kind of like a meme community. So a lot of papers in deep learning are kind of like a meme. So you have some papers like called like Elmo, which it's like a Sesame Street character, and you also have Bird, which is also another Sesame Street character, and I think there's a few other like that. And then also you have a lot of papers which are just a copy of another paper, which is something like ETS is all you need, where ETS is like some idea that you're proposing. And in here on the right, basically this is like, you can probably not see, but it's based on like someone compiled all of the papers that have something is all you need in the title. And we can see, okay, basically there's a lot of papers in that category. And the reality is that probably whatever they are proposing is not all you need. But clickbait titles are like catchy, and people they are more likely to read your paper if your title is kind of like catchy. And why do I mention that this one started this trend? Because they called it network inception. And in the introduction, they say, okay, in this paper, we focus on an efficient deep neural network architecture for computer vision, codename Inception, which derived its name from this other paper in conjunction with the famous We Need to Go Deeper internet meme with Leonardo DiCaprio. I don't know if you have seen that movie, but I remember there was one version of this paper that I think they even had like the image of this We Need to Go Deeper meme like in the paper itself. So yeah, that's kind of like Inception. And then after that, the other CNN paper that you need to know is EfficientNet. I think it wraps up this CNN stuff. They mentioned that, okay, previous papers like BGG, they show that depth is important. Inception showed that width is important. And at some point, people show that resolution of the image itself, it's also important. And this paper, they basically say that all of these things are actually important. And it's hard to design a network that actually takes into account all of these things. But they still propose like a method to do that. I don't think we need to go about the details, but the important is that all of these things are important, like both like the depth and the width and the image resolution. And then the important thing from this paper, I would say, is that they do like a kind of an in-depth study on transfer learning. And transfer learning is when you have pre-training on a large data set, like ImageNet, and then you fine-tune on a smaller one. And then basically they compare their results against a lot of other popular networks from that time. And they compare like different various version of their models on a few like small data sets, including some of them are like fine-grained data sets like Stanford cars or FGVC aircraft or Food 101. These are all like fine-grained data sets, and they have roughly like a few thousand images. And they show that by pre-training like a more large model that performs well on image recognition and just fine-tuning it, you can get very good results on these data sets. Some of these were just as good or maybe even better than specialized fine-grained image recognition models. So transfer learning, I think it's like what I want you to take from this paper. Basically, we pre-train on large data sets and we then fine-tune or do something on smaller one to get better results. Okay, so just like a short stop, like do you have any questions until here? Otherwise, let's take, I don't know, like 2 minutes or something. Okay, so can you hear me?
Yeah.
Okay,
Yes.
so I will like
Yes.
continue. So far I have covered basically, I would say, most of the general ideas that you need to know about CNNs and kind of general ideas about image recognition until 2020. This paper came out in October of 2020, if I remember correctly. And this paper is very important for all of you because all of my research is based around BITs mostly. So I will go through this paper twice because that's how important it is. And the first time I will go through it just like by skimming it, by using that technique that I mentioned earlier. Basically looking at the title. So the title is Transformers, and Transformers is like some model that was designed for NLP. And then image recognition. So okay, we already know what's image recognition. Then the structure of the paper itself is very standard. Has like an introduction, a related work, a method, experiments, and conclusion, and it has 7 figures and 2 tables. So the paper itself, the structure is standard. So let's follow it. Let's go to the first figure. The first figure describes, in this case, the architecture of whatever they are proposing. They say, okay, the model overview, we split an image into fit size patches. So they split the image into patches and linearly embed each of them, add positional embeddings, and fit the resulting sequence of vectors to a standard transformer encoder. For now, let's not focus on what's a transformer encoder and let's just assume that it's something like this. And then in order to perform classification, we use the standard approach of adding an extra learnable classification token to the sequence, which they do here. And the illustration of the transformer encoder was inspired by another paper. So if this is the first time reading something like this, you will be like have a lot of questions like what's a transformer and then everything. But remember that the goal of like skimming a paper is not really having like an in-depth understanding, but okay, rather okay, they basically propose using something called transformer encoder for the task of image recognition. That's what you should know until so far. Then the abstract dimension is the other important thing. And again, abstract usually have three different things. The first one that I highlight in yellow is the motivation. So they say basically the transformer, it was something that has become very popular for natural language processing, but they say that its applications in computer vision have been limited. And they talk about something called attention. It's usually applied in conjunction with CNNs. Attention is like the main component in the transformer. We will discuss that later. Then what do they propose? Their proposed method, they are basically saying they use a pure transformer on a sequence of patches. So they treat like an image as a sequence of like image patches. And then they pre-train on large scale amount of data and then do transfer learning. And then finally the results, they say that they say obtain excellent results compared to state-of-the-art CNNs while requiring fewer computational resources to train. So again, basically they are proposing something that using something called a transformer for image recognition by treating an image as a sequence of patches, and they say obtains good results. I think that's what you should like so far take away from this. Then if you want to like go through the paper in more detail, again, you can like go through like the results, like they usually have some tables. In this case, the tables for this paper, the first one is describing like their model details. The second one, their experiment results. Then they have like some figures describing like some experiments on different things and more effects of experiments on different things. And finally, they do some visualization of the model that they are proposing. Similar, if you remember, this is something to the visualization that they proposed in the first AlexNet paper. So why do I care so much about this paper? Because the thing is that this paper proposed something relatively simple, but they proved that it worked with a lot of experiments, which as you have seen so far, in deep learning, people care a lot about, okay, proving that something works by doing a lot of experiments. And in that aspect, this paper was just like that. They propose something simple, but they do a lot of experiments to prove that it works. And then usually when you are like doing some skimming like this, you can go directly to the conclusion. They would like usually summarize what they did. So that's what the paper summarized in the first paragraph. And then in the second paragraph, some papers they would describe some possible future work. And in this case, they describe 3 future works. One of them is you could try a BIT on other tasks like detection and segmentation. They say that you can try what they call self-supervised pre-training. And again, that's something that is out of the scope of this. And then they mentioned that you can do further scaling, so you can have even larger models. So again, like a brief summary, you go through a paper title. In this case, okay, transformers for image recognition at scale. So task, image recognition, and they propose something called a transformer. Then first figure, they are using again this thing called transformer, and they apply it on a sequence of like image patches. So they convert the image into like a sequence of like a 1D sequence. And again, like the motivation is because they say this transformer thing is very important in natural language processing, but it hasn't been applied to computer vision. So they prove that you can actually apply it if you like model the image sequence as a sequence of patches. And the condition is that you pre-train on large amounts of data. Again, pre-training is when you like you do first some training of the model on a large amount of data, and then you like fine tune it on a particular task that you care about. So that's what we mean by pre-training. And then finally they said, okay, their model obtains good results. Now about the details of the paper itself. So the motivation, again, I mentioned that there's been a lot of work on transformers, and that's kind of like the first paragraph of this paper. And they mentioned that CB, computer vision, has been dominated by CNNs since 2012. And some people, they still have tried to apply this attention, which is the key component in transformers that we'll see later, to computer vision models, but it's still like they still require on CNNs. So their contribution in the next paragraph, they describe they apply the transformer to a sequence of image patches. And then they mention that it actually performs worse than CNNs when trained on mid-sized datasets. But when you pre-training on a very large scale dataset of 14 million images or 300 million images, they say that actually BIT obtains excellent results. So that's kind of like the first page of the paper. Then the second page, again, they talk more about transformers again. If you think about it, most papers, they have something like this. They would describe the problem, and then they would like on the related work, and they would describe it again in the related work section. Just that sometimes in the related work section, they would describe this in more detail. But again, it's kind of the same thing, like transformers in NLP, like what people were doing in the past, like similar methods. Some other methods that also propose something similar, and what are the difference compared to them. And finally, they mention, okay, that large scale training actually is very important. So these are kind of like the related works. Then for the BIT itself, I will go again through this later on because again, I emphasize that this is very important that you know, but let me like briefly describe what it actually does. So the first thing is that they talk about like this patchifying or patches. What do they mean by patches? So we can imagine that if we have a CNN, what it does, it's basically applying like this, like a convolutional kernel, uh, which is, yeah, just like a learnable set of like filters over the image. The thing is like with CNNs, usually these filters are very small, are usually like 3x3 filters or maybe like 7x7 filters. In this case, what they actually do is that they use like an actual very like a convolution with a large kernel. Again, I think probably we would have to like look at the implementation of this next week for you to like fully get the details of this. But for now, what you need to know is that they apply a 2D convolution. So this is still a convolution, but the thing is like it's a convolution with a large kernel. And most importantly, it's a convolution with non-overlapping stride. So that means that the kernel and the stride of the convolution are the same. And again, I think we will probably have to go through the code of this paper, how to implement it, so you can actually get the details about it. Aside from that, they also describe that you can use like the feature maps from a CNN and directly use that like as the patches. So that's a possibility. Then after that, once you have like that like first convolution or those first set of like patches, what they do is originally this is like a 2D structure. So it's like an image. So it has two dimensions, height and width. What they do is they would like flatten this height and width so that you put all the patches one after the other. So all of these patches, like they become like one single, like 1D, one dimensional sequence. Then after that, what they would do is they will concatenate. So you have like this sequence of patches and they would like attach another like extra like token. So we can think of each of these patches as a token. If we are thinking about natural language processing, we can imagine that each of these patches represents a word because in NLP they refer to like words as tokens. So in this case, each of these like image patches, or each of these regions of the image, they will represent a token, a word. And then at the beginning of the sequence, you would attach another learnable token. And this is an idea that they took from a paper called BERT, which is again also very important in NLP, but I don't think we can talk about this. But yeah, in this paper, they proposed this idea of concatenating a learnable token at the start of the sequence. And then aside from that, they propose that in order for the transformer to learn something, because this is a sequence of image patches and transformers do not have any way of uh, encoding position, spatial position itself. What they do is they took this idea from, I think also from BERT or from the original transformer paper, where you encode information using what they call a positional embedding. And again, I don't expect you to understand this, but next week we will go over the implementation of how do you actually implement this. And then after that, the transformer, it's very simple. It's basically this block that we see. This is like one single block, and you would like stack like L number of these blocks. Usually you would stack at least 12 of these transformer blocks. And each of the blocks have the same elements. They are exactly the same. They have the same dimensions and they do the same operations, which are multi-head self-attention, a position-wise feed-forward network, and they have like layer norm and skip connections in between. And I will go over this like again in more detail later. But just to know, okay, you basically stack a bunch of these blocks one after the other. And then after that, you would apply a layer norm, which is a technique for like normalizing the inputs. And then you will apply like a small like multi-layer perceptron, like a series of like linear layers with activate like a nonlinear activation in between for for classification. And these are the equations that describe this process, and they describe it here. It's relatively short. They describe this whole thing in kind of like less than 1 page, um, because it assumes that you are familiar with transformers. And therefore, for that reason, they also included an appendix on how the transformers work. So for now, let's assume that they do this way, basically a convolution, then they attach like some things here, and then they apply these transformer blocks before doing classification. Again, we'll go through this over this later and next week. And then the rest of the paper, it's basically like a very, very long study of like transformers for like a lot of like image tasks and train on different data sets and how does that affect the results. So it's 1, 2, 3, 4, 5, 6 pages of results and description and discussion of the results. And aside from that, there's a very long appendix of, I don't know, like 10 pages or something with more results. So this is like a result driven paper that wanted to prove that, okay, like transformers, when pre-trained on large scale data sets, can perform even better than CNNs. And that was the big message that they wanted to send. And in order to prove that, they do a lot of experiments. So if you think about it, that's the same thing with ResNet. ResNet was also a simple paper. It proposed a simple idea, but in order to prove that it worked, they do a lot of experiments. So I think a lot of these landmark papers in computer vision and deep learning are like that, simple ideas where you do a lot of experiments to prove that whatever you're proving actually works. Now, this is what I mentioned, like I wanted to go over the details of the transformer itself. So the transformer, it's a paper that was proposed originally for natural language processing. So it's processing of words. And the transformer is like the underlying technology that powers ChatGPT and, well, the whole GPT line and basically every single or most of like the current state of the art models, not only in computer vision and natural language processing, but basically on most of deep learning tasks. And this paper was published by Google on this NIPS conference in 2017. It has gotten a lot of citations since then. And it's again also like a simple idea. Um, so the main contribution of like the transformer was that before like this paper in NLP, they would use something called recurrent neural networks, RNNs, and something called LSTMs, long short-term memory networks. And the thing with like RNNs and LSTMs is that they would have to process information sequentially. So you would first process like one like word, then the next word, then the next word, then the next word. And if you have many words, because you're doing this one by one, it takes a lot of time. So they proposed a method that was basically substituting that kind of sequential processing for this multi-head attention, this attention mechanism, which was already something that existed before this paper, but they applied it on this particular setting without relying on those RNNs or LSTMs that I mentioned earlier. And the thing with this attention mechanism is that you could like process the information in parallel. And intuitively, let's just say that attention, what it does, it's you're measuring the similarity between like two like tokens to make it simple. So let's say we have word one and two, and therefore like attention is kind of measuring the similarity between word one and two. Um, so why is that important? Because basically it's saying that, okay, like if this word is relevant with this other one, it's important for the particular task that I'm working on. And it kind of uses that like as a general intuition in order to uh, modify the original sequence. So if we have a sequence of words, then it will kind of modify them so that it puts more emphasis on certain parts of the words. If you're thinking about images, it makes it so that we have like more importance on like certain like parts of the word. And that's why when we have something like attention, you can visualize it like something like this. And this basically what we can interpret from this is that the model is focusing more on this part of the image, like the dog itself, or in this case, the aircraft, rather than the background. And that's kind of like what attention does intuitively. I don't think we can discuss the details of how does it do in this session, but next week we will go over the implementation of how do you implement this, and you will like probably get a better idea of how does it work. So for now, just imagine it measures similarity between two elements in a sequence, and therefore you can use this to put more importance into certain elements of the sequence. And that's kind of like the general intuition. Then aside from that, then there's also another thing that transformers do. It's called a position-wise feed-forward network. And this one I included in code because this one is very simple. So the idea is that you have a sequence, and like each element in the sequence has a certain dimension. So what you're doing is you're applying like what we call a multi-layer perceptron, which is a sequence of a linear layer followed by a non-linear activation like ReLU, as I described earlier. And then you do another linear layer. So this is an MLP. This is not something new. The thing is that in this case, they apply this MLP to each element in the sequence. And if we look at PyTorch code, this is like a simple example. Again, we'll go over this like probably next week again. But let's imagine that we have a sequence of two elements, like with byte size of two, and we have like 5 elements, like 5 words or 5 image patches in this sequence, and we have 3 channels. And basically what you're doing is you are applying like a linear layer like on this dimension here. So we are changing the last dimension from 3 channels to 12 channels. Then we apply a nonlinear activation like ReLU, and then we change the last dimension back to 3 channels. So this is what it does here. You basically increase the dimension, apply a nonlinear activation, and then reduce it again. And that's it. And actually, this can be also implemented as a one-by-one convolution. And here I describe the exact way that you can implement that. And this like one-by-one convolution to change the dimensionality of like a sequence or an image. This has been widely applied on computer vision for a while now. So before this paper came out or before the transformer paper came out. So it's not exactly something new, uh, but they call it position-wise feed-forward network. And then finally, I mentioned that they apply something called layer norm. And what you need to know about like this, there's like different kinds of norms. There's one called batch norm, there's layer norm, then there's instance norm, and then there's this group norm. And what you should know is that when we have like an image or a sequence or something, we may have very different values across like different pixels or like different values in the image. And this can cause problems when you are like doing like the optimization of these networks, like using like a stochastic gradient descent or something. So like back in 2015, like this group from Google, these are the same authors from the Inception paper. They proposed this technique called batch normalization, which was to accelerate the training of deep neural networks by basically normalizing the inputs to this layer um, across like a dimension. In the case of batch norm, they will normalizing the inputs across the batch dimension. So basically like different images in the batch, they want it to be normalized. And also, yeah, that's kind of like the idea behind batch normalization. But this paper, they use this other technique called layer norm, which again, they have the same objective, normalizing the inputs. The difference is that, well, batch norm normalizes across different elements in the batch. Uh, like layer norm normalizes across the spatial dimension and the channel dimension. So I think you can just think about it as some way to normalize the input so that it's within a certain range. And why is this important? Because this helps train deeper networks faster. That's what you should know. Again, we'll go through this like next week also, like in code implementation should be much easier to visualize. And then I'm like almost like finished. After this BIT paper, a lot of things happen, and I would say this is probably the most relevant for all of you. There was this paper called Training Data Efficient Image Transformers and Distillations Through Attention, which was published on the same year as BIT, roughly 2 months later. And they proposed a few things, but the most important thing that they proposed is a strategy to train transformers on uh, let's say relatively like smaller data sets, like medium-sized data sets like ImageNet, um, like 1K, which has 1 million images, compared to BIT, which was pre-trained on 300 million images. And this is very important because after this came another wave of papers where they focused on the importance of augmentation and regularization, which is something that a few of you will be studying. And this paper, I would say, was the one that bring this to the spotlight. They tried a lot of different like augmentation techniques. So this everything in this table are augmentations, and these are like uh, regularization techniques. And they basically try them like one by one. And they say, okay, adding this augmentation helps the accuracy somehow. And then they came up like with this new strategy to train BITs, and they obtain much better results. And here on the right, some of the augmentations that they used, like for example, this is like a image of a dog. I think this is a corgi. And then there's one augmentation that they apply that is called mix-up, where you combine two images, like you can see here. or this one is called cutout or random erasing, where you remove like a part of the image, or this one is called cut midts, and you also kind of combine two images but in a different way compared to mix up. Then there's one which is called um, like repeated augment, where you basically, instead of having like one augmentation of an image in each batch, you would have, let's say, two augmentations of an image. And we can see that for this kind of anime data set. In this case, I have three augmentations of the same image in the batch, and supposedly that helped them a lot in their experiments. And then there's what they call augmentation policies, which is basically a set of possible augmentations that you can have for an image. And in here we can see, for example, this is like the original image, and this is one augmentation, this another one, another one, another one. And there's like different augmentation policies, and they tried with a few different of them, and they reached the conclusion that, for example, using one particular augmentation policy called random augment also like was lead to much better results. So the takeaway from this paper is that augmentation and regularization is very important, and the training strategy is very important. And they focused on BITs, but a few papers after this have proved that this is very important for every kind of network. So that's something that I think you should have into account. Aside from that, after that, there's been a lot of papers on BITs. A lot of them, I won't go through them, but just to let you know, this is like a survey that someone did, and you can see that basically the number of citations or papers that have been using BITs has grown a lot in the past few years. In case you're interested, you can read it. Otherwise, it's okay. Um, then a few of you, I think, actually all of you will have to do some paper reading for like as a homework, and then I will give you some papers to read, and so I will tell you like, okay, like basically read this paper, and I want you to do like an analysis compared similar to like the ones I did before, and you don't need to like copy the screenshots from the paragraph or something like I did, but you still need to like kind of describe, okay, like kind of like the general ideas of, okay, like this is what the paper proposed, this is the motivation behind this paper, like this is the related work, and these are like the experiments that they did, and like this is like the results, like basically their results are good or something. Because this is something that you will have to do a lot, and you will have to like present like papers before like you do your final project. So I will give you like a homework to read two papers. One of them, you will read them in depth, like this one, like go over like the like each part, like okay, the motivation, the related work, the method, and the experiments and results. And I also want you to read one paper like this kind of like skimming kind of strategy, like okay, like this is what the paper title, and this is their abstract, and this is their main fear, and this is their motivation, and you kind of have a rough idea of what the paper did without going into the paper into too much detail. I will give you like the homework later, but I think that should cover. Uh, so far, we have seen CNNs, we have seen BITs, and now to like enter like one of the last sections, like the importance of scale and parameter efficient transfer learning, which is more relevant for Keysoon, but probably most of you will have to deal with parameter efficient transfer learning. Uh, so I think you should all pay attention to this part too. The first thing is that like one of these trends that we saw across all of these slides is that if you have larger models, train on more data, you can perform better across a wide variety of tasks. Not only on the original pre-training data, but you can perform better on other tasks that may be completely unrelated. And this is a trend that people have been studying for a while on NLP. And we have seen like the trend of models getting larger and larger in NLP. You have things like starting from BERT and the first GPT, and now you have GPT-3 and GPT-4, which are larger than ever. And this trend has been going on for like the last few years and probably will continue for a while. And people have been also studying this same thing has been happening on vision. So you should know that scale is very important. Like models are keep going to get bigger. So how can you like make use of these large models? And one of the ways to actually do that is by doing this parameter efficient transfer learning. In particular, there's one idea called something called adapter. And an adapter, to make it simple, is some relatively small like model, like some small like model that you like put like you train to like obtain benefits from fine tuning like the whole model at a much larger at a much lower cost. So on the right we see a table where they show how if you like fine tune like different number of layers you get better results. But if you use like these so-called adapters, you can actually get as good results as when you're fine tuning the whole model. But the thing is that you have much fewer parameters compared to like, let's say fine tuning the whole model. And this is the same thing that you see in here. When you have full fine tuning, you might get like this, like the best results. But when you use like some of these adapters and there's like different types of adapters, you can get almost as good results as the original version, but you have like much fewer number of parameters, like maybe like 5% or 10% or maybe like 15%. So it's still like much lower than fine tuning the whole model. And these kind of ideas have been designed for transformers in NLP, but they are kind of picking up pace in computer vision. So I think probably we'll have to go over this like at some other later point. And I kind of summarize here like kind of some of the general ideas of how do they do this. I don't think we can go over the details. Then there's also another like parameter efficient technique called prompt tuning. And prompt tuning is also similar to what I showed you earlier, but at the same time it's different. So we have like fine tuning where we train the whole model. Prompt tuning, we have like a frozen model, but we have like if we think about things like an NLP, like words, we have like this input text, but we can actually concatenate the input text with what they call a prompt. So it's basically a set of like some words that you can put in front of the text to make it like obtain better results. And this is an idea that people were doing manually with models like GPT-3. You would like tell GPT-3 something like, okay, translate from like a certain language and or use this like as a certain example of how do you want it to do a task. And they noticed that okay, by using these prompts like writing in a certain way, you could get better results using a frozen model. And someone decided to okay, instead of like designing yourself like some text or something to put in front of the input, you could like actually learn these like text, like what you should be saying, what you should be telling to the model, so that it obtains like similar or better results. And that's kind of like the idea with prompt tuning.